Okay, welcome back. So, hopefully it is early enough in the morning that none of you have been April fooled yet today. So keep an eye out for crazy posts or social media things or whatever. I won't do April Fool's Day, jokes on you, but I don't know about all of the all of the faculty. So hopefully nobody pulls one over on you today. The plan for today is to just continue on with section 7.2, factoring trinomials that look like this, and then start on 7.3, factoring more general trinomials, where our leading coefficient is not necessarily 1. And the quote of the day today is from philosopher David Hume, from back in, I think he was like 1700s or so. And the statement is, a wise man always apportions his belief to the evidence. And I think this is, one of our kind of fundamental, like scientific ideas, right? Is we want things to be evidence-based when we're in a scientific realm. Evidence-based medicine is a big deal today, but in general, uh, the types of support that we want for scientific statements is evidence, as we, might call it. We want empirical evidence. But I think it's also important to keep in mind, though, Hume's guillotine from an idea kind of from the same philosopher, David Hume, sometimes called the is-ought problem, that science and these evidence-based statements are very good at, quote, is statements. So statements about factual reality, if I drop the ball on this ramp and let go of it, it will take about this amount of time for it to fall to the bottom under the influence of gravity and so on. Science is quite good at statements like that, but what ought we do? Should we do this or that? That's often a more complex decision, taking into account things like societal values, trade-offs, complex trade-offs, um, all kinds of things. Um, so it's important to apportion our beliefs to the evidence, but to recognize that that statement uh, really corresponds with the kind of is side of things, perhaps more than the ought side of things. It's very easy to make an is statement and kind of mentally have that leave its lane and kind of think that it also is an ought statement. And we just have to maybe take a little more care in keeping those two separate. All right, so we started 7.2 last time. And remember, our goal was to rewrite x squared plus bx plus c, where b and c we think of as integers, as the factored form, this product of two binomials, x plus m times x plus n, where again, m and n are integers. So almost always, certainly in the context of this course, when we talk about factoring the quadratic, we're thinking that we have integer coefficients, and we want to end up with integers in our factored form as well. There might be an occasion here or there where that's not 100% true, but for the vast majority of cases, it is. And recall that the strategy we came up with to do this was we wanted to find an M and N given B and C, given what we call the cross term, the coefficient of X, and our constant term C. We need to find these numbers M and N, and just by kind of multiplying out and matching things up, we saw that M times N has to be C and M plus N has to be B. Now, this is a 2 by 2 system of equations. It could be somewhat challenging to solve, but importantly, we were looking for integer solutions, right? We're looking for integers M and N. Kind of interestingly, this is searching for algebraic solutions over the integers is in and of itself kind of its own field of math. Maybe not its own field, that might be pushing it a little too far, but a big its own kind of subsection of math. And some of these problems are actually exceedingly difficult, right? I mean, you think of like how do you solve equations? Well, we looked at solving linear equations, but that process doesn't only give integer solutions, right? It might give all kinds of solutions. But since we're looking for integer solutions, we didn't take so much of an algebraic approach as we took a uh, almost, I sometimes call it like a sledgehammer approach, like, try all of the things. So basically we looked at, well, since I have integer c and I want integers m and n, I can probably just figure out what are all of the ways to factor c, an integer, into the product of two other integers, m and n. And I could probably just make a list of that. And unless c is some absurd number, an absurdly large number, that list isn't going to be too long. I can just physically write it out. It might be a list of 2 or 3 lines. It might even be a list of 5 or 6 lines, but it's not going to be a list of 10,000 lines or anything like that. And then from this list of products that multiply to C, I find the line that adds to B. If I write out all of the products that multiply to C and none of them add to B, well, then the other positive of doing it this way, rather than say guess and check or something like that, if of all of the m's and n's that satisfy the first equation, none of them satisfy the second, well, then I've proven that I cannot actually factor that specific quadratic over the integers. I've proven that it's what we call prime. So we saw examples of all of that last time, but I'm just rehashing that to jog your memory. So that if you weren't here last time or something, review the lecture last time. So that was not intended to be a first introduction to the topic. But hopefully that jogged your memory. And now we're going to run through, we're just basically going to pick up where we left off last time, running through several sets of a couple examples, a couple exercises, going back and forth. This is one of those things that, like I had mentioned before, factoring is kind of the over the hump material in the course that if you drill this, if you put in the effort and diligence to master this material, the rest of the course will be much easier. But if you don't put in that diligence and effort, this is the material where students face the most challenge. And if you don't understand this material, then other material in the future will be more challenging. So that's why we're going to take quite a bit of time drilling examples and exercises here. Okay, so let's move on to these two examples. So we have x squared plus 11x plus 18. So I see that b is 11 and c is 18. So I'm looking for two numbers m and n that multiply to 18 and then add to 11. So I want m times n equals 18. And I'll start listing out some possibilities. I always start with m equals 1 and n equals 18 or n equals c, and then I work my way up. So the smallest m could be is 1. Could m be 2? Well, sure, we could have 2 times 9. That would be a way to make 18. What about 3? Yeah, I guess we could have 3 times 6. What about 4? And I'll write these out because we're still doing this the first couple of times. Normally we just not write them. But is there an integer multiple of 4 that makes 18? 4 times an integer is 18? No, there's not. I mean, 4 times 18 fourths makes 18, but 18 fourths is not an integer. What about 5? Is 18 a multiple of 5? No, it's not. 5 times 3 is 15. 5 times 4 is 20. If we were to keep going, we'd say 6, but wait, I already have 6 listed over here. So if I was to keep going, I would just have, 6 times 3, but I'm repeating myself here. And as you all know, I already do that enough. So at this point, I can stop. I really needed to go up to 5 because otherwise I just start repeating my previous list. Okay, so So basically I need to go up to the square root of my number is how far I have to go. And at this point I've enumerated in this list here the three ways to factor the number 18 into the product of two integers. 1 times 18, 2 times 9, 3 times 6. Now I also, in this example, want b to be 11, or in other words, I want m plus n to be 11. And if I look at each of my rows, 1 and 18, m plus n makes 19. 2 and 9, 11. That's the one I'm looking for. 3 and 6 would be 9. So m equals 2, n equals 9. That's the m and n that multiply to 18 and add to 11. And I see that I can factor this quadratic as x plus 2 times x plus 9. And if I wanted to, I can multiply it out. I could FOIL it out and just double check. I get x squared. My outer pair is plus 9x. My inners give me plus 2x, that's plus 11x. And my last give me 9 times 2 is 18. Now, one thing that I might notice is this second example, x squared plus 9x plus 18, it actually has the same c. It has the same constant term. What that means is that it's going to generate this same list of m's and n's, of potential m's and n's. 1 and 18, 2 and 9, 3 and 6. That was only dependent on the constant term. Now, which line I pick out of here is going to change, because here I have b equals 9, so m plus n has to equal 9. So now I'm not interested in the second line anymore. Now I'm interested in the third line, where the sum of m and n are 9. So specifically m equals 3, n equals 6 is the m and n that I want here. So x plus 3 times x plus 6. And again, I could I could multiply it out and double check everything. X squared plus 6x plus 3x is plus 9x, and then plus 3 times 6 is 18. So it looks good. So note that the constant term is what gives us our list of potential m's and n's, and then which pairing we pick from that list, or perhaps no pairing at all, maybe such a pairing doesn't exist in that list, is dependent on what is m plus n, right? If we were looking for an m plus n to be 10 or something like that, well, we would say this doesn't factor over the integers because we wrote out all of our m and n pairs and none of them add to 10. But in these cases, we're looking for 11 or 9, picking out two different lines from the m and n list, 2, 9 versus 3, 6. Okay, so jumping down here to a couple of exercises. So take about maybe 4 minutes or so, work through these: x squared plus 14x plus 13, x squared plus 10x plus 21. And in about 4 minutes, we will come back and discuss the answers. Okay, let's take a look at these two exercises. So the first one, we see that we have a b of 14 and a c of 13. We're looking for two integers that multiply to 13, add to 14. And really our only option for two integers that multiply to 13 is 1 and 13 because 13 is prime. So if we recognize a prime number, that really only gives us one possibility for factoring, 1 and 13. And again, I have to check that 14x, that b of 14, is that 1 plus 13? In this case, it is. So it can factor. If that cross term was anything other than 14, if it was 25 or 3 or something, then that quadratic would just be considered prime. It wouldn't be able to be factored over the integers. One little note that I want to make here is it might kind of seem like the larger that C is, the more factors we have, the more potential, lines that we have to write down. There is maybe a little bit of truth to that, but take, for instance, something like m times n equals 12, right? Actually, one below 13. For 13, we only had one line. 1 and 13 was the only option. We have 1 and 12, 2 and 6, 3 and 4, and then once we get to 4, we don't have to keep going any further. But for 12, one smaller, we have 3 different options: 1 and 12, 2 and 6, 3 and 4, right? So the primes are a little bit funny like this, or how, like, kind of in a sense, how composite a number is, how many factors that it has. It's kind of funny. Like, you could have a prime number and then, go one further or one before it or something like that, and then have a number with lots of factors that have several options, right? Or consider like 17 versus 16, right? 1 and 16, 2 and 8. Well, 3 doesn't work, but we could have 4 times 4, versus say 17, which is prime, only has one option. Now, if we have a number that's like on the order of 10 or 20 or something like that, we're not going to get, a dozen factors out of that or something. Obviously, it's just not quite big enough, but the point is, changing up or down by, say, one digit can dramatically change the number of factors that we have, say 17 versus 16 or 13 versus 12, something like that. And then for the second one, x squared plus 10x plus 21, again, looking for two numbers that multiply to 21. So we write out our list. We have 1 and 21. 2 doesn't work. 3 and 7 works. 4, 5, 6, they don't work. They're not factors of 21. And then once we hit 7, we see that we're starting to repeat back up the right side. So we have 1 and 21 or 3 and 7. And we're looking for the m and n combination from this list that adds to 10. And we see that's 3 and 7. So we multiply this, or we factor this out as x plus 3 times x plus 7, and then we can multiply it back out to check our work. We get x squared plus 7x plus 3x is plus 10x, and then plus 3 times 7 is 21, looks good. Okay, let's look at a couple more examples. So let's look at x squared plus 11x plus 30. So I see that c is 30 and b is 11. So I'm looking for two numbers, m and n, that multiply to 30 and add to 11. So 1 and 30, that's always a choice. 1 in whatever number. Is 2 a factor of 30? Yes, it is. 2 times 15. What about 3? 3 times 10. 4? No, I don't think so. What about 5? 5 times 6. And then, of course, if I go any further. I'm repeating myself, so we can stop there. I'm looking for two numbers that add to 11. So I'll make a list of m plus n. Well, this first line gives me 31, second 17, 13, and 11, and that's exactly what I'm looking for. So this is going to factor into x plus 5 times x plus 6. All right, now let's look at the next example here. Y squared plus 19y plus 60. I'm looking for two numbers that multiply to 60 and add to 19. I'm going to do things a little bit more quicker as we go along. So I want to write out all of the integer pairs m and n that multiply to 60. Well, I have 1 times 60, 2 times 30, 3 times 20. So for 60, maybe think of like 60 minutes, right? 4, what's a quarter of an hour? 15 minutes. 5 times 12, 6 times 10, 7, I don't think that works. What about 8? No. Does 9 go into 60? No. Does 10? Well, now we're back up at 10 times 6, so this is our list. I'm looking for one of these that adds to 19. And I see 15 and 4 works. So I don't have to write out my whole third column of m plus n for all of them. I can just kind of search through and do this pretty quickly, right? 61 is too big, 32 is too big, 23 is too big, 15 and 4, yeah, that's 19. That's exactly what I'm looking for. So I can write this as x, or well, our variable here is y plus 4 times y plus 15. So as we're going on here, we'll try to become a little quicker, a little more efficient with things, just to make the process go a little more quickly and smoothly. Okay, so we're going to work on these exercises. There are 5 exercises. You might initially think, oh, geez, this is going to take forever. But notice something interesting about these 4. These have different B's, but they all have the same C. They all have the same 100 for these 4. And remember our list here. Making our list is kind of the most labor-intensive bit of the whole process. But that list is going to be the same for all 4 of these. So once you create that list once and use the answer this one, you could use the answer this one, or this one, or this one. Now I did throw a bit of a monkey wrench in here. Give a little bit of thought to how these might work. I want you to try to work through this yourself. You know, I've been, I suppose, a bit disingenuous about a certain detail here. We've always had m times n equals positive number, and we've only been considering positive 1 times positive 30, or positive 3 times positive 10. Is that the only choice? Is this a list of all possible choices for m and n that could multiply to make, say, a positive 30? So maybe give a little bit of thought to that. So these first 3 will work just the way we've seen before. These last 2, there might be a little bit of a hiccup. So try to work through it yourself. Try to figure out how can we kind of adjust or adapt to what we've done so far to answer these last 2 questions. So here we'll take maybe about 8 minutes for these. The first couple should go fairly quickly, especially once you get your M and N list done. But those last couple, give a little bit of thought. How can we adjust what we've done to handle this slightly different, this new case? Okay, it's right around 7.5 minutes or so, but um, I think this should be enough time. So let's look at our first one. 48. What are the factors of 48? Well, we could have 1 in 48, 2 times 24, 3 times 16, 4 times 12, or 6 times 8. Now, one thing we can do to be a little more efficient once we get used to this is instead of writing out all of the possible m's and n's and then checking for the sum we need, we can check for the sum we need as we go along. Now, in this case, we kind of had to write them out anyway. We got bad luck in a sense, I suppose, that 6 times 8 was the last one we wrote out, but we could write out 1 times 48 and ask, does 1 and 48 sum to 14? No, so keep going. 2 times 24, does that work? No, keep going. And we could stop whenever we get a success. We don't have to check all of them. Now, if we don't get a success and continue to not get success all the way down, and then we list all of our list, if we enumerate all of our m's and n's and don't get any successful ones, then we've proven that our quadratic is prime. So while we could kind of use a guess and check method, just trying to think of two numbers that multiply to 48 and add to 14, if we fail that method, maybe if you recognize it right away, you can write the answer down. But if we fail that method, if we say, I can't think of two numbers that multiply to C and then add to B for this particular C and B, just because I can't think of two numbers doesn't mean the two numbers don't exist, right? So the guess and check method can be a quick way to get a quick answer if you recognize the answer, but you always want to know the method to kind of enumerate the entire list to fall back on in case either the quadratic factors and you just kind of didn't think of the two numbers that it might factor into, or in case it doesn't factor if it's prime, you want to be able to prove that to yourself by writing out the list of all possible combinations and showing that none of them are going to work. But nevertheless, we see that x plus 6 times x plus 8 is our answer here. Now, if I write out the factors m and n that multiply to 100, I get 1 times 100, 2 times 50, 4 times 25, 5 times 20, and 10 times 10. And for my first two here, I'm looking for a sum of 101 and a sum of 20. And I see that 1 and 100 gives me 101, and 10 and 10 gives me 20. So I get x plus 1 times x plus 100 for the first, and x plus 10 times x plus 10, or we just call that x plus 10 all squared for the second. Okay, pretty straightforward stuff. But here was the challenge problem. For my next two, I actually have x squared minus 20x plus 100. I need the sum m plus n to be negative. Or for the last one, x squared minus 52x plus 100. That c, that last constant term, is still plus 100, is still a positive number when I multiply the two m and n together. But now when I add m plus n, I'm looking to get a negative number. Is that possible? Well, sure. I can multiply two negatives together. Their product is going to be positive, but their sum is going to be negative. So this is something that I suppose that I've hidden a bit up here when I've said this is all of the ways that you could, this is all of the m's and n's that multiply to make 60. It's not really, right? We could do plus 1 times plus 60 or negative 1 times negative 60. So each of these has a negative counterpart that will give the same product. When we take that into account, we see that we can achieve negative cross terms. We can achieve m plus n being a negative number. So if I list out those five here, I've listed them out completely separately just to make the point to really drive it home. -1 plus -100 is -101, and so on. Which one of these lines gives me a sum of -20? That's the last one down here. So here, m is -10, n is -10. So then x plus m is x minus 10. And x plus n is x minus 10 again. That's x minus 10 all squared. Note the difference. This is x plus 10 squared. This is x minus 10 squared. Right, changing that plus to a minus inside of the square did not change my constant term. It was plus 100 in both cases, but it did change the sign of my cross term. Right, my outside and inside are either plus 10x or they're minus 10x minus 10x, but the lasts, I either get plus 10 times plus 10 or minus 10 times minus 10, and the negatives cancel. And similarly with the minus 52 for the cross term, I see that that turned out to be this line. -2 and -50 are the numbers that multiply to positive 100 because the negatives go away. And add -2 plus -50 is -52. So when I'm adding, the negatives don't go away. When I'm multiplying, the two negatives multiplied together make a positive. And I see x minus 2 times x minus 50 is the answer here. So just to run through some kind of similar examples to that, we're looking for m and n that multiply to 18 in this case, and that add to 4, or that add to -9. So the way that I'm going to approach this is I'm going to look for, I'm going to forget about sign first. I just want to find two numbers that multiply to make 18. That would be like 1 times 18, 2 times 9, 3 times 6. Now I know I want my product to be positive, so I could either have plus 1 times plus 18 or -1 times minus 18. Same here. And then if I'm looking for m plus n equals 4, m and n are going to have the same sign because they've got to multiply to a positive number. They have to both be positive or both be negative. Since m plus n has to be 4, a positive number, and m and n have to be the same sign, they both have to be positive, both negative, I see that m and n have to both be positive. So what would m plus n be? Only looking at the positives. Well, 1 plus 18 is 19. 2 plus 9 is 11. 3 plus 6 is 9. I'm looking for m plus n equals 4. I don't see it in this list. This is actually prime. I cannot factor x squared plus 4x plus 18 over the integers. It just kind of is what it is. Now, on the other hand, if I look at my next problem, I see I still have 18 as my constant term. So this list, I can I can reuse this list for this second problem here. But now I'm in a little bit of a different scenario for the next step. I have m plus n equals -9. Since m times n has to be a positive number, m and n have to have the same sign. They either both have to be positive or both have to be negative. If they add to a negative number, well, if they add to a negative number, they've both got to be negative. So m and n are negative in this case. So now in each line, I'm only going to look at the negative options. -1 minus 18 is -19. -2 minus 9 is -11. -3 minus 6 is -9. And this is exactly what we want here. So m equals -3, n equals -6. And let me get rid of this error that's kind of cluttering things up here. So we have x minus 3 times x minus 6. Once again, we did a lot of work here with, especially with negatives. We probably want to multiply this out and check. My first, give me x squared. Outside minus xx, inside minus 3x, that makes minus 9x, that's good. And then last, our negative 3 times negative 6 is positive 18, that looks good. So once we start throwing the possibilities of negatives around, we see that we have to be a little more careful. The strategy is more or less the same, but there are just a few additional nuances, a few additional steps that we have to take. X squared plus 4x minus 12. So again, we want m times n, in this case, equals negative 12. So now my negative sign, instead of being on the middle term, on the cross term, and having a positive constant term, now I actually have a negative constant term. How does this affect things? Give me 1 second here, sorry. Okay, so how does having a negative here affect things? Well, I know if I want two things to multiply and be negative, they have to have opposite signs. One has to be positive, the other has to be negative. I'm going to start by making my list and just kind of ignoring the negative sign. I need two numbers that multiply to something like 12. 12 versus negative 12, that's just a question of sign. Which one is positive, which one's negative, and so on. I'm going to start off by looking for factors of 12. So I have 1 and 12, 2 and 6, 3 and 4. If I want any further, if I went up to 4, I get 4 times 3, and I'd be repeating the options I already have. Okay, so these are the m's and n's that give me m times n equals 12. But then I see that because the product of two things gives me a negative number, they have to have opposite signs. In other words, m could be plus 1 if n was negative 12, or m could be negative 1 if n is positive 12. And likewise for the others. B is positive 4. The sum m plus n gives me positive 4. I'm writing the plus explicitly in front of the 4. We don't really have to do that. In fact, it's kind of bad notation to do it, but I want to be very clear about the fact that we're looking for a sum that is positive. So if I have two numbers that have opposite signs, one's positive, one's negative, and I want to add them together and get a positive, well, that tells me that the larger number in magnitude has to be attached to the positive, right? So I could have something like, whatever, 16 minus 12 gives me plus 4. The 16 is bigger than the 12, so the 16 has to be the one that is attached to the positive, and the minus 12 attached to the negative. So since my sum has to be positive, the bigger number has to be positive. So if I were to look at n equals 12 and m equals negative 1, 12 minus 1 is 11. Or if I were to look at 2 and 6, again, to get a positive sum, which is what I'm looking for here, the positive number has to be the bigger one. 6 plus a negative 2, 6 minus 2 is 4. And hey, there we are. So I think m equals 6, n equals negative 2 will work. I should have x plus 6 times x minus 2. If I multiply this out, I get x squared minus 2x plus 6x. That gives me a net plus 4x. And then plus 6 times negative 2, or minus 12. Can I do this a little more efficiently? I mean, it seemed like the way that I worked through it here, and even in this other one up here, it was a little bit kind of haphazard. I kind of muddled through it a little bit. So I might notice a pattern. Let me give myself a little bit of extra space here. If c is greater than 0, m and n have to have the same sign. If c is less than 0, they have to have opposite signs. If they have the same sign, if b is greater than 0, both are positive, or if b is less than 0, both are negative. If c is less than 0, if m and n have opposite signs, if b is greater than 0, the bigger number is positive. If b is less than 0, the smaller number is positive, the bigger number is negative. So I really have these 4 situations depending on the sign of c and the sign of b. If I figure out what situation I'm in, I don't have to write all these, like, all the different pluses and minuses and think through so much of this. I can do a lot of that work on the front end and save myself a bit of hassle. Okay, so what do I see? I see that b is negative 1, and I see that c is negative 20. So c is less than 0. We're going to get opposite signs for m and n. So when I add them together, there's a tug of war between them. One of the m or n is going to be trying to pull us positive, the other one trying to pull us negative. Which one wins out? Since b is less than 0, well, the one pulling us negative wins out. So the large number has to be negative, and the smaller one has to be positive. So I have a large negative plus a small positive. I have a net negative when I add them together. So I need a product, m times n, of negative 20. Again, I'm going to start enumerating. I'm going to forget about signs for the time being. Start enumerating all the ways that I can multiply two positive integers to make 20. 1 and 20, 2 and 10, 3 doesn't work, but 4 times 5 is 20. And then if I keep going, if I go up to 5 times 4, I've got a repeat. I can stop here. So I kind of get, in a sense, kind of the number right. And now I've got to get the sign correct. These have to be opposite signs. So one is positive, one is negative, with the larger number being negative. So these have got to be negatives, and these positives have any chance of working out here. Then what is m plus n? Remember, we're targeting m plus n equals negative 1. Negative 20 plus 1 is negative 19. That's not right. Negative 10 plus 2 is negative 8. Also not right. Negative 5 plus 4 is negative 1. And that's exactly what we're looking for. Right? So I can be a little more efficient. I can have a little bit more of a kind of a clean strategy if I abstract away a little bit and kind of realize that I have really these four scenarios. If I look at the sign of C and the sign of B, then I kind of know what situation I'm in, and I don't have to do all of this kind of crazy plus minus versus minus plus, or like plus minus versus plus minus kind of stuff, right? So I see +4 and -5 are the M and N I'm looking for. X plus 4 times X minus 5. And again, if I check, my first give me X squared. My outsides give me -5X. My insides plus 4X. -5X plus 4X is minus X. That's what I want. My last give me +4 times -5 is -20. Exactly what I'm looking for. Okay. So I think keeping this in mind is really helpful. Also keeping in mind that when we're setting up this list, the first thing we look at is just getting the number part right. And then we use our scenarios up here to get these signs right, the plus and minus signs right. And then we go through and we look to see if any of those are an actual solution. So we're really narrowing down our solution space from all pairs of integers to just these few pairs of integers to just these ones with this plus minus configuration. And then that's our search space, only a few pairs that we have to add together and see if any of them work. Okay, so let's take a look at these three exercises. Uh, so again, take maybe about 8 minutes for these three, because with these minuses floating around, these can sometimes be a little more complicated, a little more time consuming. So we take about 8 minutes for these three, and then we'll come back and discuss the solutions. Okay, it's about 7.5 minutes, so let's come back and discuss these three. So the first one, y squared minus 5y minus 6, we see that b is -5, c is -6. So c being -6 means we need the product of m and n to be negative, which means they have to have opposite signs. And we're also looking for their sum to be negative, since b is -5. So the larger in magnitude number has to be negative, the smaller in magnitude has to be positive, so that their sum is negative. So I come over here and I set up my table looking for m times n equals -6. And I start off by just looking for a list of m's and n's that multiply to 6. So I could have 1 times 6 or 2 times 3. If I go up another one to 3, 3 times 2, I repeated that one already, so I can stop there. And then I refer back over here to get my signs correct. The larger in magnitude gets the negative sign, the smaller magnitude gets the positive sign. So I have +1 times -6 or +2 times -3. And then I look at their sums. +1 minus 6 is -5, and +2 minus 3 is -1. And of course, -5 is what I'm looking for in this problem, the sum of -5. So this tells me my m and n are +1 and -6, or I get y plus 1 times y minus 6 as my factor form. And again, I can FOIL that out to check. My first give me y squared. My outsides give me -6y. My insides give me +1y. So -6 plus 1 is -5y. And my last give me +1 times -6 is -6. So it looks good. Okay. Put a check next to that one. I've checked that off. Okay, let's look at the second example. X squared plus x plus 5. So b is +1, c is +5. C being +5 tells me that m and n have to multiply to a positive number. They have to have the same sign, either both positive or both negative. And b being positive, b is +1, that tells me that they've both got to be positive. Both m and n have to be positive. If they were both negative, they would add to a negative number. There'd be no way that b could be +1. So I want to first start writing out my list of possible m's and n's. I want m times n to be +5. So I just start with finding a list of m's and n's that gives me 5. So 1 times 5, and since 5 is prime, that's it. These have to be the same sign, both positive, so that's +1 times +5. And then if I find their sum, m plus n for this only possibility is 6. But wait a minute, I'm looking for a sum of +1. The only potential sum that I can come up with is +6. Well, this is not going to factor over the integers. This is what we call prime. So we can't factor this into a nice form like we could with, say, these y's up here. So this is a prime quadratic. We can't factor it over the integers. And then our third and last exercise is x squared minus 2x minus 8. And again, we notice that b is -2, c is -8. C being -8, that means m times n has to be -8. They have to have opposite signs multiplying together to get a negative. And b being -2 means the larger in magnitude number has to be the -1 and the smaller magnitude the +1. So that when they add together, everything stays negative. Okay, so with that information, I come over here and I look for m times n equals -8. And I start off by just thinking of m times n equals +8 and getting my list of numbers before I worry about the signs. I could have 1 times 8, 2 times 4. 3 is not a factor of 8. And then if I go up to 4, I have 4 times 2. I've repeated, so I don't have to list that one. And I remember that I have opposite signs. The larger in magnitude is negative, the smaller positive. So the 8 gets the negative, the 1 gets the positive, or the 4 gets the negative, the 2 gets the positive. And then lastly, I check what is m plus n. So what's the sum of these? -8 plus 1 is -7. I'm looking for a sum of -2. That's not quite right. -4 plus 2 is -2, and that's exactly what I'm looking for over here, where b is -2. So that tells me that I have x plus 2 times x minus 4 as my factored form. And I can double check. I can take my firsts, x squared, my outers minus 4x, my inners plus 2x, so that nets to a -2x. And then my last, positive 2 times -4 is -8. So that looks right. Any questions so far? Okay, couple more exercises to get a little more practice. So we'll take maybe about 5 minutes and work through these two, and then we'll come back and discuss. Okay, let's take a look at these two exercises. So the first, x squared minus 3x minus 54. We see that b is -3, c is -54. So as far as signs go, we're going to need opposite signs because c is negative. The product of m and n have to be negative, have to have opposite signs. And we see the sum is negative, which means the larger number in magnitude has to be negative, the smaller positive. So I'm looking for m and n that multiply to 54 first off. So I have 1 times 54, or 2 times 27, or 3 times 18, or 6 times 9. And then to get my signs right, I need opposite signs with the larger one being negative. So I'll go down my n list, which has the larger numbers, make all those negative, make the m list positive, and then I'll look at their sum. -54 plus 1 is -53. That's not -3, so keep going. -27 plus 2 is -25. Keep going. -18 plus 3, -15, not -3. Keep going. -9 plus 6, that's -3, exactly what we're looking for. So there we go. We see that our factored form should be x plus 6 times x minus 9. And if I check, my first give me x squared, my outside's minus 9x, my inside's plus 6x, that gives me a net -3x. And then my last, 9 times 6, 54, with a negative sign, one is positive, one is negative. That looks right. For my second example, x squared plus 4x minus 12. So c is -12, b is +4. C is -12. That's what m and n multiply to. So they have to have opposite signs. One has to be positive, one has to be negative to make a product that's negative. And b is +4, so the larger in magnitude number has to be positive, the smaller magnitude negative, so that when we add them together, they net out to be a positive. So we come off to the side and we find, we start with just m times n equals 12. We find our factors. 1 times 12, 2 times 6, 3 times 4. Then we get our signs right. They have to be opposite signs with the positive number getting, or the larger number getting the positive. So the list of n's, the larger numbers, will be positives, and then the m's will be the negatives. And then I add them together. Remember, I'm looking for a sum of +4. -1 plus 12 gives me +11. That's not +4. I keep going. -2 plus 6. That does give me +4. And I can stop here. I don't have to write down the +1, although I suppose I could if I really wanted to. But I see that my factored form x minus 2 times x plus 6, and I can check that my firsts are x squared, that matches. My outsides plus 6x minus 2x from the insides plus 4x, so my cross term looks good. And my last -2 times 6 is -12, so this is our solution. This is our factored form. Something that we might notice is that the factored form will be unique basically up to the commutative property. So if you wrote x plus 6 times x minus 2, there's nothing wrong with that. Or if in the previous answer you wrote x minus 9 times x plus 6, perfectly fine. I suppose even if you wrote like 6 plus x times -2 plus x, that's not wrong. It's maybe just kind of a funnier way to write it. Like, most people wouldn't write it that way, but it's not a wrong way to write it. It's not mathematically incorrect. But up to commutativity like that, these factorings are unique. So it's not like I'm going to find x minus 2 times x plus 6, and you're going to find x minus 4 times x plus 3 or something that, would also work. It's not going to be anything like that. Okay. So let's look at a couple examples now with different variables here. So here we have examples with two variables. In the first case, x and y. So I have x squared plus 5xy plus 6y squared. Now, I think there's a couple ways that I could approach this. One is more algorithmically like our previous example, I can basically think of this like x squared plus 5y times x plus 6y squared. And I can look for an m and an n that in this case are going to contain some y's that multiply to make 6y squared and that add to make 5y. So if I think about this, I need m plus n to give me 5y. Well, I think that would mean that m has got to be some number times y, and n is also got to be some number times y. And that meshes with m times n, number times y times number times y, giving me number times y squared. So I want m times n to be 6y squared, and I want m to have one factor of y and n to have one factor of y. I also have to get the number right. So m could be like, say, 1y, and then n would be 6y. This is just like above where I'd have, 1 times 6, but they just have a y tacked onto each of them. Or m could be, say, 2y and n 3y. Or if I go up another one to 3y, well, that'd be 3y times 2y, but I already have that one in the previous line. I see that m plus n is 5y. So I suppose I could have plus y times plus 6y or negative y times negative 6y to make plus 6y squared. But I see that my sum has got to give me positive 5y. So these should both be plus. They have to have the same sign and have to add to a positive number, so they both got to be positive. What is m plus n? What is y plus 6y? That's 7y. What is 2y plus 3y? That is 5y. And I see there's my 5y. So I think all of this just factors down to x plus 2y times x plus 3y. Let me FOIL this out. Because it's a little complicated, we got x's and y's floating around. I'm going to actually come off to the side and write this out carefully. So my first give me x squared. My outsides give me plus x times 3y or plus 3xy. My insides give me 2y times x, or that's plus 2xy. And my last give me plus 2y times plus 3y, or plus 2 times 3 is 6. Y times y is y squared. And this does indeed give me plus 5xy, which is exactly what I'm looking for. So I'm confident I've checked my answer. So I could also use something a bit more like a brute force approach. I could say, okay, I know that the form of the factored form here is going to be like, it's going to have an a in the first term of each of the binomials, and then it's going to have a b in the second term. So it's going to be like a plus mb times a plus nb. It's got to be that way because when I multiply these out, I get a squared plus NAB plus MAB. And then plus M times N. whoops, not AB, B squared. And I see that that gives me the correct A's and B's in the correct terms. Give me 1 second here. Sorry, my allergies are just like absolutely going haywire these days. Uh, the spring with all of the temperature fluctuations and extra rain and snow and everything has uh, been a crazy allergy season. Although I feel like last spring was kind of the same way. I don't know. Um, anyway, so on one hand, I can take a very like algorithmic approach going through the same systematic process. On the other hand, I can take a bit more of an intuitive approach. And there are pluses and minuses to both. The intuitive approach, kind of when it works, it typically works a little more quickly. But if it doesn't work, if you don't see the answer right away, you might have to back up to the algorithmic approach to either get the answer or to argue that the thing doesn't factor. But I'm looking for two numbers that multiply to -12 and that add to -4. They have to be opposite in sign. So I think this is going to be like -6 and +2, right? I think it's going to be a minus 6b and a plus 2b. Does that work? My first give me a squared. My outsides give me plus 2ab. My insides give me minus 6ab. And my last give me minus 12. I just did the same thing last problem, minus 12b squared. Get so used to writing AB, it just keeps going. This does give me minus 4AB, which is exactly what I'm looking for. So I can take a systematic approach like up here. Even in a more complex case, I can use the foundation that I built up through these problems with just one variable and apply that same systematic approach with just maybe a minor tweak to a new type of problem. Or I can take the intuition that I built up and apply that intuition to a new type of problem. As a side note, I think this is really the one of the main learning points of mathematics is the ability to abstract away from the details, to understand that I've solved this type of problem half a dozen times before in my life, whatever kind of problem it is, whether it's a math problem or something else. Can I extract from that a general principle that I can apply to help me more quickly or more effectively solve problems in the future? I really think that's, much of what mathematics is, generalization through abstraction that lets us solve more problems more easily and more effectively in the future when we recognize patterns. Or when I recognize this almost fits the pattern of something that I've seen before, that means I can probably kind of apply the principles that I've applied before. And that's at the very least going to give me a pretty strong leg up on coming up with a solution for this problem. Okay, two last exercises in this section. And actually that'll wrap us up for today, given what time we're at. So let's take about 5 minutes on these exercises. That'll take us to almost the end of class. So I won't really say too much on these at the end, but we'll take about 5 minutes and then do a quick wrap up. Okay, let's look at these last two exercises. I'll go through them really quickly because we've only got a couple minutes left, but you can see all the details here. For the first one, we have x squared, and then what we think of is maybe like -8 or plus a -8y times x plus a -65y squared. So we have x squared plus something times x plus something. So our m plus n should be like -8y, and our m times n should be like -65y squared. So let's start with m times n equals 65, just to get the numerical part right. That would be 1 times 65, 2, 3, 4, not factors. 5 times 13 gives me 65. And I actually noticed that 5 and 13 are both primes. So I can either factor into the product of two primes or into 1 times 65, but those are the only options. To get my signs correct, I note that the product has to be negative, so it's got to have opposite signs. And the sum has to be negative, which means the larger of the two has to be negative. So I have -65 versus +1, or -13 and +5. And then lastly, I guess I didn't write it up here, but m times n has to be -65y squared. So m and n both have to have a factor of y, which I'll just go ahead and write in everywhere. And now I need to search in this list for the particular case where the sum is -8y. In the first case, -64y. In the second case, -8y. So I have x plus 5y times x minus 13y is my answer. And I basically do something very similar down here, with the main difference being that the sum is positive and the product is negative. So I need opposite signs, with the larger in magnitude being the positive and the smaller magnitude the negative. So that ends up selecting out -4b times +7b. The sum is 3b, the product is -28b squared, and this gives me the factored form a minus 4b times a plus 7b as my answer. Okay, let me stop the recording.